Yes, the fabled green button. Hi, everybody. My name is Sarah Martell. I am the node leader for UNSW, Sydney and Canberra. And I'm also part of the survey management group for the GALAH survey. And so I am really pleased to get to come and give everybody an update on what we've been up to lately. And it's also been, can I say, is the last day of the meeting. It's been really fun to hear what everybody's been up to. So thank you all very much for all of your great presentations. So GALAH is a galactic archaeology project, which means that in this case, it means we're very interested in the Milky Way. We want to understand it in extreme detail as a tool to understand galaxy evolution more broadly. And so our particular goals have always been to look at the Milky Way's history of star formation, chemical evolution, and accretion through high resolution spectroscopy for 1 million stars. So we've been at this for some time now. We've taught a lot of birds to look at spectra. It's going really well. We will be having a new data release later this year. And the team's been working really hard. In particular, Sven Buder, who's a postdoc at ANU, has been working really hard on getting everything together. I believe the number of stars we're putting in there is very large. At the moment, the catalogs that the team has to work with for early science and for testing there's 660,000 stars, where we are pretty confident in the stellar parameters and the abundances. But there are another 150,000 that might make it over the line before we actually make DR4 happen. So I'm pretty excited about that. So what's in GALAH DR4? What's new, right? So like I said, a lot of this work is Sven. So we've got more stars. We've got new elements. Not that there are new elements in the universe, but things that we couldn't measure before, and now we can. And we're adding globular clusters, which is something that Maddie McKenzie will talk about in a little bit. So these are the elements that we're measuring, and in our 600,000 stars that is in every panel of this plot, which is kind of overwhelming. And the things that we've added that are new are carbon and nitrogen, which are really, really fundamental, really important for a lot of studies, and are also, they don't have very nice, clear atomic lines in the optical, and so have been a challenge up until now. And so what changed is actually that we stopped looking for atomic lines and started looking at the molecular stuff. And it turns out that once we get all of our data calibration in really good shape, we can work out a nice carbon and nitrogen abundance out of the molecular stuff at the ends, the very far blue and the very far red of our data. So this is very exciting. It gives us entirely new science questions that we could not get into before. And like I said, we've got globular clusters in the data set. Now we've had them, they're one of the first things we observed, but we're actually happy with how the data look now. So this is just to show that we have a lot of mostly red giant branch stars across a range of clusters. And like I said, Maddie will get into this more later. And I don't have a picture of M82, but I do have M92, which is like 10 more. So. All right, so some of the science things that we're up to right now, and some of the things that we've published recently, I just want to give you a little tour. So Ella Wang, who was supposed to be here, but has COVID and hopefully will be feeling better soon, has been working on really detailed 3D non-local thermodynamic equilibrium stellar atmosphere models to work out lithium abundances with really, really excellent precision. And so the lithium is in the middle of a whole bunch of other stuff. You have to be really careful with how you measure it, but it's important in a lot of different science directions. And so to be able to be more sensitive, to measure to a better threshold, and also to just be more precise and more confident in our answers is a big deal. For us, we can look at aspects of stellar physics. So this is a little corner at the high mass end of the main sequence, where you have a sharp switch from the purple bit where every star has detectable lithium to the green bit where nothing has detectable lithium because there's like a convection thing that happens right at that mass. So we're seeing stellar evolution in action in a way that we couldn't do before. We also can look at galactic chemical evolution in a really useful way. So the growth of lithium over time, this is metallicity on the X and lithium on the Y, can let you look at things like novae or other processes that produce lithium in the galaxy. The other thing you can do with this is solve the cosmological lithium problem, right? So classically, the cosmological lithium problem is that the cool dwarfs sit about half a dex below where the Big Bang nucleosynthesis level is. But what we've been able to show is that if you consider the warm dwarfs as the remnant population of what used to actually have the original Big Bang nucleosynthesis abundance, all of the more metal poor stuff has evolved away by now, but there's a few stars left that still form that original, very primordial population. So GALAH can connect to a lot of the different science questions and projects within ASTRO 3D. It's been a really exciting thing for us to be part of, to be able to see those bigger pictures on all of the detail stuff we do. So you heard yesterday from Evans and from Michael that both of them are using our abundance measurements to look empirically at how particular nucleosynthetic sites work, supernovae, AGB stars, things like that. We can look at, this is more of a first stars thing, but we can look at chemical signatures of POP3 stars. This is from a study that involved Anisha Marcy, who was a PhD student at ANU a few years ago, looking for, within the GALAH data set, they found 166 stars that look like they've been chemically influenced by one pair instability supernova. And so pair instability supernovae only come from stars above 150 solar masses. They are incredibly rare things. And so to find dozens of these things gives us a really interesting ability to look at the very early IMF and the way that nucleosynthesis actually operates at extremely high mass stars. We can look at the ISM, so going from very first stars to things that haven't even formed into stars yet. Rok Vogrinčić is one of our PhD students in Slovenia, and he took all of the GALAH data and basically took out the stars and got residual ISM spectra and found 65 new diffuse interstellar bands that nobody had ever found in the optical before. And so his paper on this was just published earlier this year. It's a whole new catalog of, we don't actually know what they are, right? The thing about DIBs is they're probably large carbonaceous molecules, but we don't actually know. So again, it's just giving us wonderful new directions to go into. The history of star formation and chemical evolution in the Milky Way is a thing that we always say we want to get into. Sanjeev Sharma, who was at Sydney Uni for a number of years and has moved over to Space Telescope recently, has put together out of GALAH data these evolution trends for different elements. So each panel here, we've got carbon and oxygen and magnesium and silicon and calcium. And the x-axis is age of the stars, so the oldest stars are on the right. And he split it up by metallicity to see if at different metallicity, those elements are evolving differently with time. And they mostly aren't, which is a bit odd because you expect your sources of nucleosynthesis to evolve a bit as your stellar population ages. But one of the things that we can do with this that's really interesting is compare to models. So this is a paper from Jaya Carrillo, where they have the exact same information, but from their galactic chemical evolution model. And so we can look for places where we agree or disagree qualitatively or quantitatively and try to figure out what's going on there. So this is stuff that this was just published this year, so we haven't really gotten into it yet. But there is most definitely enough information in GALAH to really get into that. I also want to point out that to get the ages to do this kind of work is a whole magic trick in itself. And so the ages in Sanjeev's paper were mostly sort of a Bayesian isochrone analysis kind of thing. But Jo Cusa, who's at ANU, she's a postdoc at both RSAA and the computer science department, has put together some really excellent tools for inferring age information directly from spectra. So this will be a thing that we will get into in the near future and have a lot of fun with trying to work out age determinations and seeing if we could do a better job, because age is one of the most difficult things to get for individual stars. Dan mentioned this earlier, that we can use both kinematics and elemental abundances to identify stars that probably formed in dwarf galaxies and then were later captured into the Milky Way. So this is something that Sven published last year, where he looked for the best abundance combination in order to understand which stars are which stars are local, and which stars migrated from other galaxies. The thing I really want to point out from this is that if you do a chemical selection, you get one set of stars. If you do a dynamical selection, you get a different overlapping but different set of stars. Both of these ways of thinking about accreted stars are incomplete and contaminated. And so this is a high dimensional problem that requires a more complicated solution than drawing some boxes in a plane. We'll get there. I guess the last science thing that I will mention is that, of course, as Amelia pointed out, this is one galaxy. And while we love it very much, and we know a lot about it, it is in fact much more useful to be able to use what we know about the Milky Way to think about other galaxies. And so I want to highlight Primordial Wang, who's a PhD student at Sydney, and Luca Menerens, who is an honor student at ANU, who's talking next. Both of them are working on the idea of translating between resolved stars and unresolved stars. Primordial is putting together the data for what if you observe the Milky Way with an IFU, which I'm very excited to see how that's going to go. And Luca is doing direct comparisons of individual star studies versus resolved star studies. So this is all very exciting. We need to be able to translate both directions to get the most out of either data set. So I'm very excited about that. And also, this is why we're all very into geckos. So looping back to what I said in the first place, our science goals are, and always have been for the last 10 years, to look at the history of star formation, tick, chemical evolution, tick, accretion, tick, through high resolution spectroscopy for 1 million stars. We're working on it. We got a lot of them. We'll get there. Thanks very much.